Before we continue with trigonometric equations that are quadratic in form, I thought we'd review some of our quadratic tricks that we have from algebra. Recall that all of these trigonometric equations that we're doing use the same principles as algebraic equations. So we can have a trig function that looks like a quadratic function, and that means that we can use techniques we've used in the past. So looking at our quadratic equation, I'm going to bring out what I call my toolbox. There are four basic techniques for solving quadratic equations. One is the zero factor property, one's the square root property, one is the completing the square process, and the fourth one is the quadratic formula. Starting with the zero factor property, this is typically the easiest if you can see how to factor something. This zero factor property gives us comes from the fact that if we have two factors whose product is 0, the only way that can happen is if the first factor is equal to 0 or if the second factor is equal to 0. And this goes for as many factors as you've got. So if we can factor this left side's expression into two binomials whose product is 0, which we already have a product that's equal to 0, then we can use the zero factor property. And in this case, I notice that my 2 and my 3 are, if you add those two numbers, you get to -5. And so I'm going to try putting 2x minus 3 times x minus 1 equals 0. When I do that, I get 2x times x is 2x squared. 2x times -1 is -2x. -3 times x is -3x. So when you add those together, you get -5x. And -3 times -1 is +3. Now at this point, we know that the only way this can be true is if 2x minus 3 equals 0, or if x minus 1 equals 0. Now I have two equations that I can solve, and 2x minus 3 equals 0 would mean 2x equals 3, x equals 3 halves. X minus 1 equals 0, add 1 to both sides, we get x equals 1. So we've got two solutions to this equation, which we solved using the zero factor property. We're going to use this a lot. It may not look exactly the same. Sometimes when we factor, we may end up with something like, say, sine theta cosine theta minus cosine squared theta. Well, this doesn't factor like we would expect, but we can still factor out a cosine theta, leaving us sine theta minus cosine theta. And that gives us two factors whose product equals 0. This is a little more complicated because of the sine and cosine in the same factor, but it's doable. Moving on, let's look at our square root property. Square root property says that if you have something squared equals something else, then the thing that's being squared, typically we see it written more like x squared equals a, then the thing being squared is equal to plus or minus the square root of the right side. So in this case, I have an x plus 3 that's being squared, and that's equal to 7. And what that means is that x plus 3 must equal either positive or negative square root of 7. And at this point, I'm still trying to get my x by itself, so I will subtract 3 from both sides, and I get x equals -3 plus or minus the square root of 7. This is two answers. If we needed to write them without the plus or minus, we could say x equals -3 plus the square root of 7, and x equals -3 minus the square root of 7. And the square root property is handy when you have something like, say, sine squared theta equals 1/2. Then you take the square root of both sides and you get sine theta equals plus or minus 1 over the square root of 2. And if you've played with this enough, you'll realize this is the same as plus or minus square root of 2 over 2. So that's one time when it would be easier to use the square root property when solving a quadratic. Finally, sometimes we have to use the, I call this the sledgehammer of Quadratic Toolbox, because it's a beast of a tool to use, but it will tear down any project you need to tear down. The first thing we need to do is recognize that when we talk about A, B, and C, we're saying that A is our leading coefficient, B is our coefficient in front of our linear term, the term with no exponent, and C is our constant term. And one thing I neglected to do on this is I should have said x equals, because that's how we find our solution. So looking at this, we can say x equals, b in this case is negative 4, so the opposite of negative 4, plus or minus the square root of negative 4 squared minus 4 times 3 times negative 2 all over twice a. So x is equal to 4 plus or minus the square root of 16, that would be plus 24 all over 6. And that gives us plus or minus the square root of 40. That is 4 plus or minus the square root of 40 all over 6. And when we were doing these back in algebra, we would say to go ahead and simplify this mess completely. So that would give me 4 plus or minus the square root of 40 is the same as the square root of 4 times the square root of 10. So it would be plus or minus the square root of 4 is 2. 4 plus or minus 2 square root of 10 over 6. Factoring a 2 out of the numerator, we get 2 plus or minus the square root of 10 over 3. Factor 2 out of the numerator and divide the numerator and denominator by 2. Now, this is not what we're going to need with trig, though, because if we have an equation that is so messed up that we have to use the quadratic formula, we're going to be looking for something we can plug into our calculator. We won't be saying x equals this stuff. We'll be saying sine theta equals all of that nastiness. So we're going to need something we can plug into our calculator. So what I'm going to do is say 2 plus the square root of 10 equals, divide that by 3, equals, and so I get one answer that is x equals about 1.7207597 or 5922, and the other answer would be 2 minus the square root of 10. And again divided by 3. Negative 0.387. 4258867. So let's do some examples that actually use this quadratic toolkit within some of our trigonometric equations.